Okay, let's continue. So in the previous video, we know if we have a random variable and we want to estimate its distribution, and we are lucky that the sample space is small, then just count the for each value, just count the proportion of the observed data, and then we're done. But when the sample space is large, then it's not that easy. Like if I still look at the 731 days in the past 2 years, but now I let X be the daily bike rental, then in that case X, even though it can still be said to be discrete, but the sample space contains more than 8,000 possible values, right? And it would be hard if we just want to count the frequency for each possible value, okay? When the number of historical data points is much less than the sample space, then that method would just be not okay. So now we're going to do frequency distributions first instead of just count frequencies. And then we're going to do that with classes. So basically, what we want to do is to construct the frequency distribution or frequency table. And that method is just identical to what we need to do for a histogram. Okay, so given X, I have those historical data and I have the 731 daily bike rentals. Then I'm going to put those 731 numbers into these 9 categories or 9 classes. I divide the possible region into 9 classes and then put numbers into those 9 classes. Then I'm able to create this frequency distribution. And for each class, I can count the proportion of values that happens in this class. Okay, these values are just the relative frequencies that we did for frequency distribution. Like for this particular value, it's obviously 18 divided by 731, and so on and so on. Okay, so instead of calculate the probability for each value to occur, I now calculate the probability or proportion for each value to occur in that class, occur in one class. Okay, then with this frequency distribution, I actually can calculate the probability for the value to be less than or equal to a given level, which is my CDF. For example, I probably is in particular interested in a value that is 3,500. Okay, I'm looking at this particular value. What's the probability for capital X to be less than or equal to 3,500? Well, according to my definition of CDF, I know what to do. I'm going to calculate the sum of the first 3 categories, which are here, here, and here, right? And for the last category here, I'm going to take 1/2 of it, because when I do frequency distribution, I assume all the values spread equally possible within that class. Okay, so that means I'm going to sum up the first 3 values and then plus 0.073 into that particular probability. That's going to give me roughly 0.308, okay, according to my histogram or according to my CDF. So that means given the 731 values, I first create this frequency distribution, and then for each given value, I use my definition to do the calculation. Okay, so I'm using this proportion distribution or the frequency distribution to be my probability distribution. Okay, so that makes sense, but that's not very useful in many cases. There are at least two reasons that we don't want to use that 9-class distribution. First, the calculation is actually not very easy. Okay, we cannot have a simple formula that directly gives us a number given a particular level that we are interested in. Or we cannot use functions or Excel functions to do it very quickly. So that's one thing. It's hard to be used. And also, we know in any case, it's just obtained from a sample. So given that the 9-class distribution is from the sample, it has no chance to be exactly the probability distribution of that random variable. So that means some adjustments are fine as long as we do that in a reasonable way. So now I'm going to do what people typically do when we do distribution fitting. We're going to fit a theoretical distribution to the observed distribution. What does that mean? We're going to ask ourselves to believe that the population follows a certain distribution. We have no idea what that distribution is, but we probably look at the histogram of from the historical data and use that to guess what's going to be the population distribution, and then try to see whether our guess is right or wrong. So we're going to try to find a theoretical distribution that can represent or that has a high chance for us to see the observed values. Okay, and that process is called distribution fitting. So to fit a distribution to our histogram, we're going to first select a distribution, either by investigation or by experiences, and find the theoretical frequency of each class according to our hypothesized distribution, and then put the two things together to see whether there is a huge difference or not. So we're going to have two things. Using the histogram, we're going to have a set of observed frequencies. So we observed that a few numbers exist in the first class, a few numbers exist in the second class, and so on. And at the same time, for our hypothesized distribution, we're going to calculate the theoretical frequency. If our hypothesis is right, how many values should exist in that particular class. If the two sequences are close to each other, then the fitting would be said to be appropriate. Even though we do have some theoretical methods to judge how close they are, but we're not going to talk about it here. All we need to do is to intuitively verify whether they are close or not. If we want to visualize the quality of our fitting, we probably want to depict the assumed and hypothesized and observed distributions into a graph, and we're going to typically make them two frequency polygons so that we can see whether they are close to each other or not. And then we may try a few distributions and select the best one. So let's see an example. Suppose that I want to fit a theoretical distribution to the daily bike rental example. Then, according to this black curve, that black curve is the observed frequencies. So I know, well, from 0 to 1000 I have something, from 1000 to 2000 I have something, and so on and so on. So if I say I want X to be uniform within 0 to 9000, what does that mean? That means I believe that the daily bike rental would be a random number between 0 to 9000. For each possible value in this region, the probability is the same. If that's true, then for the class between 0 to 1000, the theoretical frequency would be around 80. From 1000 to 2000, that's around 80, and so on and so on and so on. Because we believe each value has the same probability to occur, then for each region, for each class, it should occupy about 1/9 of the total frequencies, which is around 80. And then we compare that, we compare 80, 80, 80, 80, 80 to 18, 80, 74, 107, 160, and 6, and so on and so on. So we do see two curves here. And our conclusion would be natural. We will not say that the two distributions are close to each other. X does not seem to be uniform. On the other hand, let's try to do a normal distribution. Actually, this makes much more sense because the graph, the histogram just suggests that. So we need to choose a mean and standard deviation, and we're going to simply select the sample mean and the sample standard deviation. If you don't know how to do this, just check your previous videos. And if you don't have other better options, just stick with your sample mean and the sample standard deviation. Okay, then I have a hypothesized distribution. I guess for daily bike rentals, it's a normal distribution with mean which is around 4,500 and a standard deviation around 1,930. If that's the case, then for each class, I'm going to calculate the theoretical proportion. If this is really a normal random variable, then I should know the probability for that random variable to exist inside 0 and 1,000, 1,000 and 2,000, and so on and so on and so on. And if that's really the probability for X to fall inside the region, then in the past 731 days, that should give me a frequency, a theoretical frequency, which is around 25. And then in the next category is around 45, and so on and so on and so on. So I calculate the theoretical frequencies according to my hypothesized normal distribution. And then I may again plot the observed frequency and the theoretical frequency. The red one is the theoretical frequency if that particular random variable follows a normal distribution. In that case, we would see, oh, they look somewhat similar. We probably cannot say that X is really normal, but at least we can say, well, using normal to fit is much better than using a uniform distribution to fit, right? If you're going to guess one distribution, you're using normal instead of using uniform, because using normal seems to have a much smaller error. And then some further trials or adjustments are always possible. So let me make a quick summary. What we want to do is to estimate the theoretical probability distribution of a random variable. We have no idea about that because that's a property of the population. So we use sample to do the estimation. When the sample space is small, we only have a few possible outcomes. Then we just use the relative frequency of each possible value to be its estimated probability, or at least be a reference. When the sample space is large, then we're going to first construct a frequency distribution and use the relative frequencies of each class to be its probability. Okay, that's our estimation. And then we probably want to look at the histogram and guess which probability distribution fits it. If that's the case, then we're going to have a probability distribution, use that to calculate theoretical frequencies for each class, and then compare the theoretical frequencies and the observed frequencies. Okay, so basically we are comparing the theoretical frequencies and the frequency distribution, which contains the observed frequencies. And then we stop when the overall difference is small enough. So typically, we would try a few and then select the one with the smallest total error. And sometimes we need some human judgments. Okay, so that's about fitting. Thank you.